Okay, so let's do a very blitz review of what we did last time. So by the way, I checked the sign of the relationship between the p squared and the L squared operator that I gave in the lecture, and it was correct, okay? So what did we do previously? So previously, we saw the following things, and these are things that we'll need today. At the end of previous lecture, we found out the relationship between the p squared operator, but the combination that is useful for us is p squared by 2m, and that, of course, is minus h squared by 2m, the Laplacian operator, right? And that we found is related to the L squared operator expressed in spherical polar coordinates, and that's given by h squared by 2m. And then the second derivative with respect to r being the radial coordinate,
Sir,
and then
sir,
yeah?
Are you writing something?
You can't see it?
No, sir.
What about other people? Can you guys see it?
Yeah, I can see it.
Okay.
Yeah, I can.
Moon, maybe you can rejoin.
Okay, sir.
Okay. So let's see. Okay. And then there's a term with the first derivative with respect to r, and then minus 1 over h squared r squared L squared. Okay. All right, Moon, welcome back. Can you see the writing now? Moon?
Yes, sir.
Sorry? Sorry, can you be a bit more loud? I can't hear you. Moon, can you see the screen share? Okay. Acha. The other thing I wanted to ask you is the screen flickering for you?
No, sir, it's fine.
Okay. Acha, take it. All right. So this is the relationship between the p squared and the del squared operator. Okay. Now, always when you see something like this, you will want to make sure that it's dimensionally correct. Okay, so you need to make sure that that's one of the easiest way of making sure you didn't make an obvious mistake, right? So see that inside the bracket, everything has dimension of 1 over length square, right? 1 over length square. Here we have, so this has the dimension of angular momentum squared, which is cancelled by h squared here. So this is 1 over r squared. So everything is consistent. And of course, this has the same dimension, right? So dimensionally, it's correct. So this is something we derived last time using the fundamental commutation relationship. So that's formula number 1. We also derived the expressions for the angular momentum operators in terms of polar coordinates. And we found that Lz was pretty easy to derive. There was a geometric way of deriving Lz, and it was given by minus I h bar del by del phi, phi being the azimuthal angle. Okay, and then we also had L plus and minus, the raising and the lowering operators, and they were given by minus I h bar e to the power plus minus I phi, then plus minus I d by d theta minus cot theta d by d phi. Okay, so this is useful. And the L squared operator, to compute that in terms of the spherical polar coordinates, we need to express it in terms of Lz as plus L plus and minus. So if you do that, we get LZ squared, then we get plus of half bracket of L plus, L minus, the anti-commutator of L minus and L plus. Okay, and if you do the algebra, it just becomes minus h squared within brackets 1 over sine squared theta del squared del phi squared plus 1 over sine of theta del by del theta times sine theta del by del theta. Okay, so there is no explicit dependence on phi. I mean, there's a phi derivative, but there's no, the coefficients don't depend on phi. So these formulae will be useful. Okay, so this is our review from last time. So now what we're going to do is that for rotationally symmetric systems, we can take the we can take the Schrodinger equation, and there is a very nice separation of variable for rotationally symmetric systems. Okay, so we are going to do the separation of variables.